EIP-7212 is the most underrated Ethereum improvement proposal out there, and I can't believe more people aren't talking about this. In this video, I'll explain exactly what this proposal is, what it would mean for Ethereum, and how it is potentially one of the biggest changes Ethereum will ever have to make. This one's going to go super deep, so strap in, like the video if you enjoyed this content, and subscribe to the channel for more videos. Let's do this. So for those of you who don't know, EIP-7212 is this, precompiled for EIP-7212 curve support. Now, if you're like me, I read this and said, what the is that? And spent pretty much the whole day reading this proposal, reading about elliptic curves, how signing messages and private keys work in Ethereum. And I want to show you everything that I learned in this video, and then we will go through some little demos to actually show you what this would look like in the real world if this proposal was to go through. Before we dive into the specific details of this proposal, we first need to understand a couple of fundamental topics to how Ethereum works. The first topic we're going to talk about is accounts in Ethereum. And accounts are really just a cryptographic pair of keys of a public key and a private key. And you're probably familiar with this if you've ever used a wallet like MetaMask, for example. The way that these usually get created is you actually first generate the private key, usually just using random characters. So you generate a random 64 hex characters that make up this private key. So let's say I have this as my private key, EBAA, EDC, etc., etc. It's a big long string of numbers and letters, 64 hex characters that were generated randomly. Through some process, we need to take this private key and generate something that looks like this, which is the public key. So we generate the private key. Through some process, which we're going to talk about next, we need to end up with a public key that is related to this private key. Okay, so somehow we take this private key, let's generate a random one, and you can see every time I change the private key, the public key changes. So there's a relationship between private key and public key. By the way, thanks to this website creator, Anders Brownworth, this will be linked in the description. We're going to use a couple different demonstration applications that he has on his website. Now, the way that these two are related is using elliptic curves, or elliptic curve digital signature algorithms, ECDSA. The goal of the elliptic curve is to create a trapdoor system, meaning you can recover the public key given a private key, but you can't get the private key given a public key. The best way to describe this is with Minecraft. So right here, I have the private key. And with this trapdoor system, given that I know the private key, I can go through this trapdoor system and I can figure out the public key. But given the public key, I can't go back through this trapdoor and figure out the private key. So it's a one-way relationship. You can figure out the public key given the private key, but you can't figure out the private key given a public key. So an elliptic curve looks something like this, and it is symmetrical on the x-axis. And I'm no mathematician, and I'm not confident enough to explain this properly, so I'm going to give you the version that I understand, and I will link a resource in the description for like a 10 to 12 minute explanation in detail if you actually want to understand this properly. I'm no mathematician, like I said, so I don't want to give you any misinformation here. But my understanding is you know your private key, right? That's the entry to that trapdoor. With the private key, you need to derive the public key somehow using this curve. So basically you have a starting point, and then you start drawing these lines or reaching a new point on the curve n number of times, and n number of times is determined by your private key. So let's say you draw this line, you intercept with the curve here, you go down here, you then draw another line which intercepts here, you repeat this kind of line drawing. It's not really line drawing, obviously, it's just maths under the hood to reach new points in this kind of formula. Eventually, using this process, again, I know I'm kind of dumbing this down, I'm not in-depth mathematician, so this is my understanding, but eventually, given the private key, you do this n number of times to reach another point on this chart, which determines your public key. This video linked in the description explains it way better than I can. It just takes like 8 minutes, so I don't want to flood you with information too early into this video. If you are interested in an explanation, please check out this one. Now, regardless of if you want to go into the details of how these curves work or not, the important thing and the reason I'm bringing up any of this private key, public key, and elliptic curve stuff is because these elliptic curves and the way that you generate the public key, private key pairs comes in different shapes and sizes. And I didn't actually know this, but there are two primary elliptic curves that are relevant to us to understand. The two different kinds that we want to understand are EIP-7212K1, which I'm just going to call K1 for the rest of the video because I keep stuttering on saying the full thing. And the second kind of curve that we care about is SECP-256R1, which I'm just going to call R1. So K1 and R1. Now, in this article by John D. Cook, which will be linked in the description again, credit goes to him, he talks about this tale of two elliptic curves. And the one that's used in the context of Ethereum is SECP-K1. So K1 is used in the context of Ethereum to perform this process of generating the public and private key pairs. It's also used to verify messages that were signed by private keys. We'll talk about what that means in a second as well. Importantly, the elliptic curves come in different shapes and sizes. So there's different ways to actually derive the public key from a given private key using these different elliptic curves. So for example, K1, the K in the K1 curve stands for Koblitz, which I'm pretty sure comes from this guy. Neil Koblitz is a mathematician from Harvard and Princeton. Is known for elliptic curves, so I'm pretty sure that's where the name comes from. Anyway, regardless, the K has kind of predefined values for the formula here that makes the elliptic curves. So the formula for elliptic curves is y squared is equal to x cubed plus ax plus b. If you Google that, it looks like a much prettier version of the elliptic curve that we just drew over here. So this is the formula in general for elliptic curves. But as you know, from high school, at least I know, the values that you plug in here kind of shape how the graph looks or the curve looks on these charts that you make, right? So the values for this formula in the Koblitz version of the curve are predefined. So for example, set to a is equal to 0 and b is equal to 7. Whereas the R1 curve, the R in R1 stands for random and has these different kind of options available for the values to be plugged in. Okay, so given a private key, we now know you can use this elliptic curve to generate a public key. And the specific curve that gets used in Ethereum is SECP-256K1 or K1. An important note here is the K1 variation is almost exclusively used in the context of blockchains, whereas the R1 variation of the elliptic curve is used almost universally in every other form of cryptography and things like your mobile phone and your computer. Now we're going to come back to that thought in about 1 minute here, but I first want to show you something important about your private key, and that is how it signs messages. So if you've ever used a blockchain application before, you've probably signed a message or a transaction. The way that you do that is you first probably sign into your wallet, you approve or confirm a transaction or sign a message via the wallet interface, such as your MetaMask wallet. So this under the hood, your private key is actually signing this message, and that is outputting a signature. So let's copy this box here, and let's say the signed message from the private key outputs a signature. From the signature, you can actually derive where this signature came from, and you can also derive whether or not it was signed by a given private key. So you say, okay, it was signed by wallet number or account number OX123 and the public key. And then you say, well, let me actually verify whether or not this wallet's private key signed this message or signed this transaction. So it's a cryptographic way of saying whether or not someone actually signed a message. And this is really a high-level overview of how all transactions are kind of signed off on in the Ethereum world. So let's go back to this Anders Brownworth website here. And you can say, let's say I want to sign a message, it says hello world. In this message field here, here is an example private key that I want to sign this message with. If I click sign, here is the message. So this ends in AE619. If we go over to this, this is the signature, EIP-7212 in the signature, so the signed message of hello world from this private key. Let's say we're a different person and we receive this message signature. We want to verify whether or not this wallet address 0475249 actually signed this with their private key. What we're going to do is perform a verification process, and we click verify. You can see the green suggests, yes, this is a valid signature that says this public key verified this message. But if we change this message to say, Jared steals 100 ETH from you, I never signed this stuff, right? I never used my private key to sign this message and say, yes, I agree to what this message says. So if we try and verify something that I never signed, this is going to go red because I never actually signed that. And this signature is not actually verified correct. The same applies for the transactions here. So if you've ever tried to send funds from your wallet to someone else, you sign that transaction. So let's say I'm sending $20 from 0475 to 04cc. Here is my private key again. The MetaMask transaction or wallet transaction will pop up and say, hey, here's the cost. You're actually sending $20 worth of ETH to this wallet address. You click confirm. By doing so, you're signing that transaction with your private key and you output a message signature. This message signature is going to go to the kind of Ethereum world and the nodes running the Ethereum software. I'm kind of simplifying, but essentially it goes to the Ethereum system to say, hey, let's actually verify this signature that we just received that says you are sending your friend $20. And if you verify that, it is correct because this signature says, yes, this private key of this sender approved this transaction. If you try and modify this in any way to say, oh, you actually sent me $20,000, it's not going to go through. Or this was actually going to my wallet address, so I'm stealing this from you or something. It's not going to go through because you didn't sign that message, and this signature verification process is what's kind of going on under the hood to make sure that system maintains the kind of integrity that you expect. But why am I showing you this, right? Why does this matter? The important thing here is that that verification process assumes in Ethereum that you are using an account that was generated using the K1 elliptic curve, which is kind of unique to blockchain environments, right? Specifically, it's used in Bitcoin and specifically it's used in Ethereum and other blockchains, of course, as well. Once Ethereum receives these signatures, it's basically asking, okay, here's the public key that this apparently came from. Let's go ahead and actually verify whether or not this signature was approved by the private key of the sender of this transaction. Okay, so it's basically asking, hey, Jared, did you actually sign this transaction that you apparently sent to me? And it does this using the elliptic curve. So at Ethereum, it assumes you created a K1 account, a public key and private key pair. And it basically says, well, I'm just going to draw this on the chart in the way that I understand. Hopefully it makes sense to you as well. But again, please check out that resource in the description for a proper understanding on the actual curve and the math behind it. But from my understanding, it basically says, okay, I've got this signature, right? My job is to say, well, hey, Jared, did you actually sign this with your private key? If you did, then I'm going to go ahead and execute it. And the way that it does this, at least in my kind of mental model here, is it says, well, over here, I have the signature, right? I have the signature and I have the sender of this transaction or the sender of this message in the form of a public key, basically where this came from or who's initiating this transaction or who's claiming to have signed this message. So let's say the public key of signer. So basically, let's say this is me. I used my private key to sign the message. I send that signed message in the form of a signature, and who it came from is basically that public key of my private key public key pair. Over here, the way that I like to think about it is it says, well, given this information, then X must be true, right? And then given that, well, if I go down here, then Y must be true, right? And it does this, and it assumes at the end of this, right, it reaches a yes or no decision based on the signature if your private key of this public key signed this transaction or not. So basically, is this transaction real and signed by you or not. That's all that's happening. The important thing to note, and why I've given so much background information on things like this K1 elliptic curve, is Ethereum is assuming and it's using the K1 curve to perform this verification process. So it assumes you have a K1 generated public key, private key pair, and then it uses the K1 curve for this verification process as well. So let's revisit what I said a couple of minutes ago. Ethereum and Bitcoin and other blockchain technologies are pretty much the only ones using this K1 variation of the elliptic curve. The R1, the random variation of the elliptic curve, is used almost universally for everything else, right? This includes things like Apple's secure enclave, which is a very secure way of storing private keys and other sensitive information on things like your iPhone or your MacBook. It's also used in things like Android's key store system, which is essentially the equivalent of what we just talked about in the Apple ecosystem. The interesting thing about this is, in Apple's case, I haven't actually read too much on Android just because I am an iPhone enjoyer myself. It actually has specialized hardware that is separate from the main kind of storage hardware that is specifically designed to securely store these kinds of private and sensitive values and allows you to generate those keys in that secure enclave, for example, in a place where it is never seen by the kind of main storage or main compute area of the actual hardware. And that's not all. We're also seeing it come to the web in the form of WebAuthn.io. I will leave the links to all these in the description, of course. This is also coming to the Google world in the form of passkeys. The point I'm trying to make here is it has reached massive adoption worldwide. So the question is, why did Ethereum not use this curve, right? And the answer to that might surprise you. It is a bit sketchy. Okay, so you remember how the R in that EIP-7212 R1 elliptic curve stands for random, right? Now, the random, the EIP-7212 R1 kind of standard came from NIST, the National Institute of Standards and Technology, a US Department of Commerce. So there are rumors that at least from my understanding, have never been confirmed, that the NSA, the National Security Agency, which I believe is an American thing. I actually just found out about these two now. I'm not American myself. These are allegations, of course. I don't want to get in legal trouble or anything like that. I'm just telling you the rumors that are on the internet that I'm reading. So the rumors are that the NSA may have used its influence over the NIST to insert a backdoor into the random numbers that were selected for the EIP-7212 R1 curve. And again, I don't believe this has ever been confirmed. I'm not saying this is the truth. I don't want to get into trouble. This is not my opinion. This is just what I'm reading on the internet. So just want to make that clear. So although we can't say for sure, probably safely bet that this was an influence in the decision that Satoshi made when Bitcoin was created to use this K1 variation of the elliptic curve. And then you can probably safely say that Ethereum decided to follow suit of Bitcoin and also use this K1 variation, which is kind of unfortunate because it is different from the rest of the entire world, essentially. Okay, so the point of all of this background information is to say, if you want to use the cryptography kind of hardware from devices that people actually use in the real world, like an iPhone, like an Android, like a MacBook, like Google Passkeys, for example. Long story short, you can't do that, right? If you're generating a private key, public key pair via hardware that people are familiar with, like the Apple iPhone secure enclave, that private key, public key pair cannot sign transactions in Ethereum and have them verified. So we face this big problem today where users are forced to create public key, private key pairs using software that is completely new to them, like MetaMask or Coinbase Wallet or other kind of wallets that support this K1 creation of keys. which is a big issue for onboarding users. Just to give you a taste of what this user experience would look like, let's take a look at the documentation for protecting keys inside the secure enclave, which is the iOS or iPhone version of this kind of specialized hardware for securing these sensitive values such as private keys. So it says here, the secure enclave is a hardware-based key manager that's isolated from the main processor. So it's actually isolated separate hardware from the main processor to handle every day-to-day operations, right? To provide an extra layer of security. So when you protect a private key with a secure enclave, you never actually get the plain text key, making it difficult to become compromised. Instead, you instruct the secure enclave to create and encode the key and later decode it and perform operations with it. Now, this sentence is amazing to me, right? You only receive the output of these operations, such as the encrypted data or the cryptographic signature verification outcome. So you get the signature. The way that I interpret this is you never pull the private key out of the kind of secure specialized hardware and get it in a place in memory where it's vulnerable to some kinds of attacks or be able to read by the application in plain text, right? It goes into the hardware, performs the operation required, such as signing of a message, and you never see the private key. You only see the output of that operation, which is the signature in this case. As we scroll down further here, you can see it only works with NIST P256 elliptic curves, which is the National Institute of Technology. I can't remember the S, the organization that we looked at earlier. This is the R1 curve, right? The random curve. So it only works with the R1 elliptic curve, which is what we've just been discussing. And this is used for creating, first of all, and verifying cryptographic signatures. So you can both create the public-private key pair using this R1 curve, and you can verify the messages via the R1 curve. You actually can't put stuff that you already saw into the enclave, and that's an intentional design decision because it wouldn't be secure if you could just create stuff that you already read and had access to and then chucked it in secure enclave. You actually need to create the key inside the enclave, and then it kind of stays in that specialized hardware from its inception. Even more exciting to me is this section here, specify access control. And you can kind of read through this on your own time. Will be linked in the description as well. But this sentence here says by specifying the private key, this sentence here, you can also combine the private key usage flag with other flags to obtain additional protection for your key. For example, if you include the biometric any flag, you can instruct the system to make the key available only when the system can authenticate the user with Touch ID or Face ID. So imagine you're wanting to sign a transaction. You want to send your buddy some $20 worth of Pol or of ETH or whatever you're doing in a Web3 application. You use this extremely familiar UI of the Face ID or the Touch ID, depending on the hardware that you're using. You approve that, right, with that familiar flow. It goes into specialized hardware, uses the private key that you never have access to in memory. You never pull that out of the secured hardware. It signs the message for you based on your approval, based on your biometrics, gives you the signature in a form that you can access on the kind of main processor, right, inside of your application that you're building. And then you send that signature to Ethereum. The only issue is Ethereum can't handle the signature, right? The transaction won't be verifiable in Ethereum. But what if it was? So I kind of lied a little bit with typical EOA wallets in Ethereum, externally owned accounts, which is pretty much every account in Ethereum that you're probably familiar with. If you've used MetaMask, you created an EOA, an externally owned account. But earlier this year, account abstraction was implemented via Ethereum Improvement Proposal 4337 into Ethereum. And this allows the creation of smart contract wallets. And within smart contract wallets, you can program any logic to both handle the signature, and you can also provide any value you want for that signature. So that is almost the two perfect criteria for handling R1 signatures. Okay, so what we're going to talk about next is how account abstraction can kind of address the limitations of externally owned accounts, EOAs, that exist today because they are built with that K1 curve, can't verify R1 signatures or messages that are signed by the private keys of R1 generated wallets, or accounts rather, I should say. How can account abstraction solve this? Why it isn't really viable right now? And then we'll loop back finally to what the Ethereum Improvement Proposal 7212 is really all about. And then we'll wrap it up with some final thoughts and we'll tie it all together. By the way, I do have this video on my channel about account abstraction if you're not really familiar with what I'm talking about and the differences between EOAs and smart contract wallets. Essentially, EOAs is everything we've talked about, the public key, private key pair that can pretty much essentially just sign messages and sign transactions. And smart contract wallets are capable of pretty much doing anything, right? Anything that you can put into code, a smart contract wallet is capable of doing. So we're going to talk about how account abstraction works, and then we're going to see how we can utilize it to actually implement SECP 256 R1 signature verification. Okay, so what we're going to do is first explain how account abstraction actually works at a high level. Again, I do have another video on my channel about EIP-7337. It kind of gives a high level overview of what the vision is, what the purpose of the proposal is, and it was actually merged into Ethereum earlier this year. So the users, right? Users submit these new kinds of special transaction or meta transaction or pseudo transactions, I should say, that are called user operations. So user operations represent essentially it's kind of basically just a transaction, right? It contains things like a signature, it contains things like what you actually want to do on the blockchain. Essentially, you can imagine it as almost the same as a transaction. Importantly, this contains a signature field. Now, these operations go into what's called an alt mempool, which is what the name of the EIP-4337 is actually called, account abstraction via alt mempool. I'm not going to draw the full thing on this diagram here because I don't think it's super important for what I'm trying to get across. But essentially, it goes through this process. It goes through the alt mempool, gets picked up by a bundler. The bundler takes the operations sitting in the alt mempool, bundles them up, and submits them to a smart contract called the entry point. The entry point basically says, yo, I got the transactions from the bundler. I'm going to go ahead and try and execute these user operations, essentially their transactions that perform some actions on the blockchain, right? The entry point basically takes the transactions and sends them to the smart contract wallets that are apparently going to execute them. So let's kind of skip all the middle steps and pretend the user operation just goes through that process. So let's maybe make a note here that says bundler entry point, so we just don't skip it, but I don't want to go too much into detail. So it goes through the bundler, through the entry point. Eventually, it's going to reach your smart contract wallet. So let's represent that here, smart contract wallet. And what the smart contract wallet is going to do is it's going to call two important functions. And these are the standards. It doesn't necessarily always do this, but this is a pretty standard behavior. So first, it calls a function called validate user op, user operation, validate user operation. Hopefully that's kind of self-explanatory. And the second thing it does is calls execute. And again, execute's hopefully pretty self-explanatory. So what execute does is it basically says, I'm actually going to execute the operation, right? Give me the details of the operation. I'm actually going to go ahead and do that, right? So first it says, let me validate this user operation. And you can put anything in this validate user operation function to determine whether or not you're going to reach the second point, which is execute, right? So first you say, hey, I got this user operation. I'm going to run some logic to say yes or no. Am I actually going to run this thing? Then if you've decided to run it, you're going to run the execute function, which actually runs what's contained within that user operation. So we're most interested in this first point. So validate user op, because execute's kind of self-explanatory, right? So validate user op. Let's kind of zoom in on this function. So as you'd imagine, validate user op accepts a user operation as an argument. So it accepts a user operation as an argument. And importantly, within that user operation, there is a signature field. So the user operation actually contains the signature. Now I'm going to show you a code example. It might be a little intimidating if you're not a dev, but I'll bring it over just so you can kind of see a real life example here. So here is an example from ThirdWeb's implementation of account abstraction in ERC-4337. Here, if we zoom in, here is the validate user op function. And basically it says, hey, did this actually come from the entry point? And then it says on the second line here, validate signature. If we take a look at what this is doing, it is implementing this, which comes from the inherited account core, which is this function here. So it calls a validate signature. Within validate signature, it's saying, is this a valid signer? This function actually just says, is that address, is that public key an admin set on this smart contract wallet? That's really all that's happening. Is it says inside validate user op, hey, is the address that we extracted from the user operation signature, the public key, is that address, is that public key an admin? If we take a look at the 4337 specification definitions, you can see on this line, it says the signature field is not defined by the protocol, but by each account implementation. If we scroll down to the details here, signature is just of type bytes. Okay, so it can be any byte, which really just means you can pretty much put whatever you want in this field. And then within that function, to validate the user operation, you can say, okay, I'm gonna get the signature out of the user operation, and I have a bunch of bytes now, so I can do whatever I want in that validate user op, right? I can pretty much say, hey, let's just accept anything. I don't even need to use the signature if I don't want to. I can write any code in there, such as verifying a K1 or an R1 signature. So back over here, nothing's changed, right? It still accepts a user operation as an argument, and that has a signature. That signature could be a SECP-256-R1 signature that came from, for example, a public key private key pair that was generated in the secure enclave on an iPhone device, for example. Okay, so if account abstraction smart contract wallets can already do this, then what is the issue? Why do we need EIP-7212? In Ethereum, and in the EVM or the Ethereum virtual machine, there's this concept of precompiled smart contracts. And essentially, as you can see here, on top of having a set of opcodes to choose from, the EVM also offers a set of more advanced functionalities through precompiled contracts. These are a special kind of contracts that are bundled with the EVM at fixed addresses and can be called at determined gas costs. So essentially, it's kind of a pre-optimized function call for common actions that you would perform in a smart contract. And you can see actually the very first one here called EC recover is an elliptic curve digital signature algorithm public key recovery function. So given a signature, you can recover the public key of the wallet address that was signing that signed that signature, right? So basically you pull out the wallet address that the signature was signed by. And you can actually see this in the validate signature function that we were looking at previously, where it's recovering the wallet address, the public key of the signer, so who signed the message contained in the user operation. So essentially, for the built-in and native curve, the K1 curve to Ethereum, the EVM has a precompiled smart contract that substantially lowers the gas fees and makes a standardized way of performing this common action of recovering the public key address from a signature that is signed using this K1 method. So while it is possible using an implementation that you make or a GitHub repository that someone else has made in Solidity to recover the public key of a address that signed a message with a SECP-256-R1 curve, it is possible. The gas fees are just going to be substantially higher because it's not natively built into Ethereum and it's not got its own precompiled smart contract to make that huge gas optimization. An interesting paper on this is pronounced by this author. I don't want to insult you by getting your name wrong with my terrible Australian accent and what I think is a French name, but it describes the gas fees associated with SECP-256-R1 and how you can kind of make it optimized. In a nutshell, the key takeaway is it's significantly more expensive to do kind of the exact same thing with R1 in verifying signatures than it is with K1 because it's missing that precompiled smart contract. Here is a lovely sentence from this paper, and it says it is around a 50x factor increase to 1 million gas instead of around 21,000 gas, which is a 50x increase compared to doing the same thing from K1 to R1 because it is missing this precompiled smart contract. So finally, we do a full loop to what we were talking about at the beginning of the video. EIP-7212 creates that precompiled smart contract that we have for the K1 curve and implements it for the R1 curve. So hopefully now this makes sense, right? A proposal to add a precompiled contract that performs signature verifications in the SECP256R1 elliptic curve. What this means is you can create a private key public key pair on all of the kind of massively adopted hardware that exists today, like the Apple iPhone, the MacBook, the Android phones. Use the native hardware to those systems that is specifically designed to store these private key values securely. Use those to sign messages in ways that users are familiar with, using things like biometrics to access and perform the signature generations like Face ID on your iPhone or Touch ID on your MacBook. Sign the message. The private key is never pulled out of that secure hardware in that process, and then send it to a smart contract wallet, likely using account abstraction with EIP-4337. Have that smart contract wallet function, likely in the validate user op function, have that accept the signature, perform the R1 signature verification with this precompile to massively reduce the gas fees associated with doing this exact same process right now. Essentially, 7212 is a optimized kind of precompiled contract to perform this signature verification with a curve that is substantially more adopted universally than the default K1 curve. Now, to be completely honest with you, the details of how this precompiled smart contract is implemented goes a little bit over my head, but you can see there's some familiar stuff that we've talked about in this video, to talking about the motivations being, hey, this curve's adopted by Apple Secure Enclave, WebAuthn in the web world, Android Key Store in the Android world, passkeys in the Google world, and describes exactly kind of how this precompile would work if this proposal were to go through. One last thing I'll add is this SECP256R1 curve support for the precompiled smart contract is also recently, around 20 days ago, a Polygon improvement proposal. And that's actually how I found out about this. Is this proposal is currently being discussed on whether this should be implemented in Polygon's proof of stake chain and Polygon's ZK EVM chain as well. So go ahead and join the discussion over on the Polygon forum as well if you're interested. With that said, thank you very much for diving into the 7212 rabbit hole with me. I hope you enjoyed it as much as I did. If you enjoyed it, please don't forget to hit the like button to help me in the algorithm, reach more awesome people like you, and subscribe to the channel if you want to see more like this. With that said, thank you for watching again, and I'll see you in the next one.